you need another metric in order to assess that is not data set dependent. So I gave this example in my other class. I don't think I talked about it in here, but you're taking a picture with a camera, right? And you have, you know, there's depth of field with like regular old school camera, right? So you've got your F is high, so you can have the aperture open. What happens is that you're only in focus in a small plane, in a small area of the total visual space. Right? So as you adjust it, some things are in focus and some things are out of focus. There's a characteristic there that we're concerned with, or at least interested in, with respect to the idea of autofocus, right? So autofocuses utilize a mechanism, right, to adjust that focal value. How is it that they find the focal value? So you've got your camera here looking at it, right? You've got some objects here in this space, and as I adjust it, right, maybe this is my initial case. We'll call it T0, right? I adjust it, run it over, and now I have a secondary case, T1, right? And they go, okay, not great, but maybe I'm actually just slightly closer to where I want to be, right? So big chunk of pixels out of focus. This one's slightly less, all right? So let's do this first, and I'll talk about another scenario that's problematic that I see here. I just brought up in my own head. So I say, okay, I did this, okay, overcorrected, so let's bring it back, right? And I have another one here, right? So T2, say, okay, that's better, not perfect. Adjust just slightly over, right, until I center the item I'm looking at T3. Okay, how did I get there? How did I get there? Iteration, but what was I iterating based on? Does anybody know, like how autofocus usually works? So most autofocuses work off using something called the Laplace transform, which finds the hard edges, right? It's essentially a frequency transform associated with the sharpness of transitions between objects, between elements. Okay, so the sharpness for the Laplace transform is not a scalar value. From scene to scene, so if I take this picture or if I take this picture, when I run the Laplace transform on that frame, I'm going to get entirely different values for upper and lower. What the ideal value is going to be different for this frame than this frame. So there, it is a value that is only consistent within the frame of reference. The RSE is, right? So relative to the characteristics of the data set to data set are going to have some different variances, different relative spread. They're going to have different degrees of linearity.
Right.
And essentially, one might have more linearity or less linearity. One might be linear with partial nonlinearity, right? So what we say is when we get up later on and start doing higher dimensionality stuff beyond the strict linear, we're going to end up even being able to compare RSE or MSE from one frame to the next frame, right? It is delta T that informs us what the next process of the iterative step is. So you can look at this as a bit of a gradient descent problem as well, right? So we're looking at attempting to optimize on the surface. So we said, here we were fairly high, right? And here we were fairly high. So what we're going to hope for is that we come down with maybe a local and then another maximum, right? So as you continue, this would be the relative error of the position of the focus. Focus in too far, you're out of focus. Out too far, you're also out of focus. But somewhere in between, we optimize into a value that is the best one we have. We would say that if I reprojected this as a line, I might have first this line, right? Then this line, right? Then maybe this one that's slightly off axis, and then maybe one that goes through the actual system, right? So I'm refining it. I crank it, and I crank it back, and then I refine. It's a bit like dropping a ball bearing in a skateboard park, right?
Right.
And eventually it sets at the bottom, okay? So part of what we use RSS for and RSE for is iterative improvement. We determine whether or not we're moving forward towards a minimization of error relative to the minimization of the RSE value. Now, what happens with R squared? R squared removes the standard deviation, removes the spread characteristics by taking out the sigma, right, RSE of sigma. It also removes X bar, the mean of X, and Y bar, the mean of Y, meaning it recenters it around the origin of the axis, right? So now everything is all treated equally. Essentially, R squared is an assessment of quality that can be compared value to value, data set to data set. So an R squared of 88% on one data set and an R squared of 88% on another data set could be said as having equivalent quality fit relative to the distributional characteristics of the data we're working with.
Okay, so
I have now made an apples to apples comparison.
View R squared not as a decimal, but as a percentage?
Correct, yes.
Okay.
Because
I
what's the
didn't
max
see
value?
that.
What's the max value of R squared? 1.
1.
That's 100% perfect
Right.
fit, right? Now I say that's it's an overvaluation, but yes, you could evaluate it as a percent. I tend to evaluate it as a percent.
Okay.
Right? It's the percent quality fit. Now, what is a 1 with regard to perfect fit? I don't know. Right? We don't really know. What perfect fit would be is overfitting, or a data set that's perfectly linear or non-noised. I mean, you know, we're essentially, look, real data is never going to have an R squared of 1, right? And an R squared of 0 would essentially be data that's perfectly distributed over the entire data space.
And there's no
such thing. There's no such thing as either of those two things, right?
Okay.
That's everybody standing in a room, putting their arms out and turning in a perfect circle so that nobody touches anybody else, right? Perfect equidistant points from one another. Describe nothing. They describe entropy.
Well,
they describe the heat death of the universe. Okay, that's the end of every particle is at arm's length from every other particle, and nobody's moving anymore. All right, that's the end of everything.
So then back to the RSE, if I went through like 15 or 20 different data sets trying different features to get different responses. Some of them were giving me stuff as...
Yeah, I'm glad to see that you took the time, but it was maybe more than what I was thinking would happen. But
Well, I was
just
looking
pick
for
to go.
something that would work, and I was trying to understand the mechanics. And on Road, which is one of the mass data sets,
Yes.
I started, the first couple times I did it, I was getting an RSE of 280, and I finally eventually got it down to like 55. So is that good, minimizing it?
That seems like a pretty significant reduction.
I had to cut out some of the features. I started with all the features and then started chopping them off.
Okay, so
and then trying different
you're already getting
combinations.
up to something that we're going to be working on later on, I think, because of the fact that we discussed it briefly, but I don't think there was a feature selection section in that lab. There's a feature selection lab later on after classification. We actually have a section.
I say features, predictors, but I kind of interpreted predictors as features in this
Features and
sense.
predictors are synonymous.
Okay,
Okay, we use the term feature. Feature selection is the generic term.
okay,
That it's okay. Sometimes some things are interchangeable with regard to terminology. Other times there's like a fixed word for it.
okay,
So when I use the term, reason why I use the term feature more frequently than I do predictor is feature is more common in naming, right? So
Okay.
if there's a specific name for it, like feature extraction and feature selection are two precise terms that refer to exact operations.
okay,
They don't use the term predictor selection or predictor operation, though they could, right? There's like a proper name for it. How do the proper names come about? They come about because somebody named it, right? They did a thing, they wrote a paper on it, they came up with a name for it, it becomes standardized and accepted. So that's the reason why I say it. But there is one other thing I want to mention here, and that is with regard to this particular system, there is one weird thing that can happen here, and that is the initial T0 and the delta of T0, and let's say T1. Let's say that these two were actually equivalent to one another, right? That the actual focal value was halfway in between those values. So it's just some weird quirk of the circumstance You were under focused at the same length that you focused out. And you got the same, essentially the same error value at both points. Which way do you go?
You don't know.
It's uncertain. It really is. It's completely uncertain. It's unresolvable because you haven't learned anything. So if you get the same, if you adjust values and you get the same RSS somewhere else, you go, what happens? Now what do I do? Right? That can't happen. You can have two regions of the error surface that can have the same relative error, right? Even with a massive readjustment of the system. Now, usually is a question of how far down that error estimator goes to be able to have them be totally equivalent to one another. But that's where I say it is possible, so what do? You just put in a hard and fast rule that says if I'm approaching the maxima of either end of my system, I don't want to push toward the maxima. I will always attempt to come back in toward the center point. So most focuses start toward the center of their focal and then either move out or move in based upon what the center is. So they make small adjustments and determine whether they're likely moving forward towards the right direction. So it moves out and then moves back, assesses whether or not moving closer is better or moving further is better for the focal length, and then moves in the direction that it's assessed. So you sort of look around up here, right? You assess the area a little bit, and then you determine whether or not this is generally down. So you have to actually make an initial adjustment, or initial assessment, with one delta 1, but based upon your initial random location. You have to make some initial assessment in order to converge at that level. I'm talking about the iterative version of the solution. The version that you guys are implementing is not exactly iterative just yet.
It didn't feel like
it. It isn't. It is not iterative. It is a closed solution, right? Because it takes into consideration one, calculated metrics like sigma and the means of the values.
Right.
So those require pre-calculation, and they also encounter the entirety of the data set. So when you're globally minimizing based upon an aggregator. It is iterative in that sense. It keeps adding the values in. But on your level, it will always converge to the same value. It's iterative, but it's convergent iterative, meaning that there's a unique solution. It has a monotonic characteristic to it. So that ideal with regard to linear assumptions is really nice. It creates that confirmation of value. So that answer all your questions, or
I think so. It gives
we
me
spend a whole day talking about questions. I don't care. That's
well, it gives me a good thing to keep in mind when I'm like testing different data sets, different features, predictors, and the response that I'm trying to get, because
yes.
I quickly determined with each data set what I was going to try to use it to determine.
Mm-hmm.
And then that seemed to often not come out the way I wanted it to.
Well, that's part of it from a certain perspective, that oftentimes we have sort of expectations of what we're building for, and occasionally you'll sort of have to reframe it.
Right.
But we don't really have all the tools to be able to fish all data streams yet.
Right.
So part of you guys going out and sort of exploring that space is maybe an elucidation for later on that I tell you, hey, we're going to actually do some things that are going to fix some of the problems you're dealing with. Right, so which features are the best features? That was related to the idea of the feature selection that we talked about, the forward sequential and backward sequential versus best set. Those are all assessments correlated with the quality of that set of features relative to the minimization of RSS for an array of different versions of the features relative to the versions of different models that they came up with. Right, so there is a best one, but you're not always going to find the best one. Right, it's not guaranteed to find the best value. Sometimes the best value is all features, right? And that's just a circumstance where we have to give up something. We have to give up the precision characteristics of low variance within the data set for the high accuracy of output. Classification is often very, very sensitive to that aspect, that I must provide it with all the features in order to be able to have the best overall performance across the entirety of the data set distribution. All right, so we were discussing credit data. I think we had gotten up to the discussion with regard to, we had started with the legit scale projection, right? That's the last slide we had on. Okay.
Or
so,
right, we might have skipped ahead a little bit, but I think that's about
maximum log likelihood. Yeah, that's true. Maximum log likelihood, and then we were discussing the output factors. Yeah, okay. So I think I was bouncing back and forth between this slide. So the individual predictor P of X, that probability estimator based upon this slight nonlinearity by applying the logistic solutions. Because the logistic is not a strict linear, right? It has linear components, but it is not a linear. So by adding that log characteristic, that slight nonlinearity, I get a little bit better performance in the transitional spaces with regard to my confidence. How confident I am at that classification is reflected, and that confidence, the quality thereof, is actually as useful, or maybe even in some cases more useful, in the output as a result of what we're discussing with respect to these values, right? So if I'm the operator that's picking up your call for customer service when you're getting ready to buy your, new couch or whatever, and you're at, let's pick Nebraska Furniture Mart, right? They have their own in-house credit people or whatever, maybe they have like a company, servicing company. So you're working for that servicing company, and your job is to develop for them an algorithm that will work for their uninformed, like service people, right? They don't know exactly what all these metrics are. They're not experts in credit servicing. So currently, they're talking with a customer that has a $1,000 balance. The customer is looking to purchase a $1,000 couch, right? What happens? The initial assessment comes back, they plug it in the system, they say, oh, currently, they're likely to default as 0.06, and they go, absolutely, I'll go ahead and loan you another $1,000. You did great with the last 1,000 you had, so why wouldn't it be an indication currently that you're gonna do great with the next 1,000? But what happens with the next 1,000?
It pushes them up closer to default.
So look, if you look here, if we converted this to a 0.6, right, that's a relatively small rounding up. So 0.006 gets converted to 0.6. This literally is like a 1 times per 100, essentially perspective increase, right? So it's 100% per perspective. It's multiplying by the 1,000 you get. So you multiply by 1,000 and you get it shifted up almost at that point in time, right? It's like it goes from 0.006 to 0.6 percentages, okay? So you're you're less than, so what is that? 6 out of 1,000 goes up to 600 out of 1,000, okay? That's a big leap. So what are we going to do there at that point in time? So we start off with the assessment that adding that other 1,000 on there is not going to be that big of a deal. But whenever we actually do plug it in, we recognize that it's radically increasing the risk. So if we were to do this with regard to a projection system, we might project it for the previous design, talk about the customer's history characteristics, and then project it for the final consideration, and then allow a customer service rep to be able to determine whether or not that increase in value, it's still not 100%, right? That person's not going to default. Long-time customer, good quality, customer. You want to retain them. You don't want to tell them no that you're not going to let them buy the couch they want. So if you think that they may still buy it back, we're only just barely tipping our toe into the area that might be an indication that they would have an increased risk. So I would say maybe, depending on the customer's payment history, you can consider this. But if you did this with the fixed output, what would happen to this value? What did we set the threshold at? If we have to go back a little ways.
0.5.
Yeah. Because this is a binary classifier. Exceed 0.5 and you might as well be a 1. Binary doesn't allow 0.5. Right? So you're either a 1 or a 0. So when we're doing it within the continuous or quasi-continuous space, the reason why I say quasi-continuous is because probability isn't technically fully continuous with respect to this logistic function, right? It has continuity centered around that value. Because you're continuing to move up and continuing to move down in a finite area around the outside of the actual transition of the log scale function. So what I say is, I can keep moving, right? But this is still digitized. It's still, we're doing a digital computer. It's not fully continuous. But we have tiny decimalized values that allow us to extract out intervals of likelihood that are as informative or even more informative than the pure binary output that would occur. So we go from totally no likelihood of default to full likelihood of default, right? But full likelihood of default is only a slight wandering into that space. All right, so let's talk about the next one. Everybody good with what we're talking about there? Okay. Let's talk about the next one. Is interesting item is that student as a predictor is going to replace our previous understanding with respect to the idea of income. Saying you're a student actually changes your likelihoods. What happens here? We note that if I look at the coefficients, I have a relatively small offset scale and a relatively high correlative factor of 0.40, right? And a p-value that is not, it's not tiny like the one we had with the balance characteristic, but it's still well within the range of statistical significance of 0.0004, right? So it's still small, really tiny. Standard error there is 0.11, so the variance with respect to these this distribution is low. And if I say likelihood in default and likelihood non-default, what this is an indication of is that students may actually positively affect your ability to repay debt, right? So as a student, you may actually have better debt repayment capacity. We noted that when we included that as a predictor, individuals could take on more base debt without defaulting. So it actually implies a small shift, a small offset in the global maximum that an individual can take on without transitioning, hard transitioning. So what did we talk about beforehand? It's like that beta naught coefficient. It shifts the value of the system slightly up, right? The halfway point actually gets shifted up for individuals that contain students within that predictor database. Now, what does this become? This is not a strictly, like a strictly two-dimensional expression like we were looking at beforehand. We have an intercept, we have balance, and we have income. If both of these are logistic, we now have a three-dimensional logistic function, right? We have a logistic surface occurring here. And it's a very interesting one because if you're not a student, you have one logistic. If you are a student, you have a different logistic, right? It's a different curve that you apply to because your subgrouping, your characteristic within that distribution changes the regression function. So now we're saying that we have an initial regression as being modified by an additional characteristic. So why would this make sense that if you're a student, you can take on more debt? I think maybe just from the perspective of students are used to taking on debt, right? So student loans kind of create that sort of debt like bubble. It also might be the consideration that students have in most considerations from a classical education standpoint, fewer expenditures, and thus have a little bit more disposable income to be able to direct toward repayment. But at the same time, they have less income total, so I don't really understand how some of that could become a factor. I don't
Could it be due to the lack of data showing the defaulting because of their...
It could be that they're given more leniency.
Right.
That's a potential indication, and this is one of the problems with statistics, is that oftentimes we find correlations that qualitatively indicate certain outcomes, but we don't have quantitative characteristics that explain to us, that are explainers to the underlying phenomenon, okay? This just says there's a link between being a student and being able to take out more debt without defaulting. You draw your own conclusions from there. And the reason why I say that you draw your own conclusions is statistics are a methodology, they're a mechanism by which we attempt to inform individuals how to process information. This is a primary example of the fact that the statistical and the modeling capacity of the system is not intended for you to draw conclusions from it. you get the data, you process the information, trends and correlations are implied by mathematical mechanisms. And then you as the human individual must again imply large-scale correlational factors to try to determine why you think this is happening, right? Matter of fact, what I see is, as I look at statistical information, my brain is automatically attempting to go, this is why I think this might be happening with respect to the underlying mathematics, right? My brain's automatically filling in those details, right? So we consider student factors to actually be confounding because students tend to have higher balances than non-students. So their marginal default rate is higher than for the non-students, right? But for each level of balance, students default less than non-students. So essentially what it's saying here is students actually tend to have higher balances. And it also says what marginal default rate is an indication of the shifted period, meaning that they over the band, which is their median to their maximus, on either end, the upper and lower reaches, are actually slightly more spread out. But with that consideration, relative to the shift as a whole of student to non-student, we notice that non-students have less total value centered around their likelihood of default, and students have more center value around the likelihood of default. What happens there in the idea of saying that the marginal default is higher? I have no idea. That's an interesting conundrum because, as I say, it's a confounding factor. When you have an individual that has less disposable income and maybe more overall requirements, they are going to look at it from the standpoint of, just take it on and pay it off later, right? So it's a deferral mindset. But at the same notion, how do we get this to do something useful for us, right? We say that multiple logistic regression, or utilizing a higher dimensionality expression of the system, will actually allow us to see these two curves of the balance characteristics, in which the regression for the student and the regression for the non-student have different logistic output values. You have two different models that are bifurcated based upon this consideration. We can't treat all of them at once or all of them together. And by actually splitting them apart based upon that factor, we reduce some of the uncertainty characteristics that were actually present in the combined data set. So the multiple logistic regression will create higher accuracy classifications for likelihood of default in both student and non-students by treating them separately, by including this qualitative feature as a predictor, right? So we can attempt to predict whether somebody's a student or not by determining whether or not they defaulted at a specific rate, or we could input the value that they are a student in order to turn it into two separate models. Each of these becomes a data set we run a logistic regression on. Each of those become the space in which the logistic regression is calculated and characterized, and by that we create a more comprehensive or more accurate model. Now, is this common that we can do this where we say we have clear underlying relationships of performance with certain individual characteristics of the data set? Not all the time, right? Not all the time are people easily sorted into in and out camp with regard to the likelihoods or events here. Also, note that even with students involved, though we see band differences, is it as stark as the difference between income and balance with respect to the predictors? No, income and balance were virtually indiscernible, right? Here we still do see some differences between student and non-student that are fairly visually easy to see in terms of separability, that there is an underlying factor. However, over the entirety of the range of the system, over the full range, they're pretty tight to one another. We see the upper band still stops in about the same range, and their means, while shifted slightly, are not too far off of one another, right? So the mean of the non-student group is right around that $700-ish mark, and the mean for the student group is around the $1,100 mark. okay, about $300 difference. The upper limits on both of those go from between like 450 to I think it's 450 to 480, and then the upper limit being somewhere in the neighborhood of about 1350 for the student group. So the spread that we were experiencing or seeing previously for student and non-student in a combined approach is actually going to be narrowed and will give us a better ability to predict the default likelihood for both cases. However, as I said, the marginal default likelihood for the students is higher. So what do we do there? We say, yes, I'm able to get some information out of it. Yes, it provides me some detail, but what does it actually provide me detail with? It's telling me that non-students actually have, on average, less capacity to take on debt than the students. So in truth, we've actually brought down the value of the mean of that halfway point of the marginal likelihood for non-students. So now that I know if you are a student versus non-student, I'm less likely to say non-student, I'm less likely to give you more money than I am if you are a student in this case. But I still have to consider the fact that it's not going to be a huge relationship. All right, so we have a couple of things we're going to look at here. We're going to look at the South African heart disease data. This was actually in the previous set of slides, and it gets covered in this chapter again, right? We use the same data set twice. The last one was an attempt to do some kind of linear predictive capacity with it. I don't think it works well at all. Matter of fact, I think it's kind of a bad example, especially when we consider how hard it is to do with regard to classification. So we say we have 160 cases of MI, myocardial infarction, which is actually just a heart attack, right? We'll include them as a heart attack. Within that case space, we have 302 controls. So we have a total of 462 total samples in the data set. 300 are controls, 302 controls, 160 are case factors. We want to be able to separate the individuals, right, relative to the predictor risk characteristics. So we say overall prevalence in this region is very high. Prevalence of MI is 5.1%, means 5% of the population is actually experiencing some sort of MI heart attack event in that space during that period, right? That's a huge amount. That's like 3 times the national average in the US. Okay, so we're going to use 7 predictor characteristics, and we're going to look at a scatter plot of those 7 predictor characteristics. We saw something like this. Matter of fact, I think we actually saw this same graph without coloration in it in the first set of slides for Chapter 1 review. Now we're looking at it from the perspective of seeing how the data is actually corresponded to being in the group versus non-group. So cases, heart attacks are red, and non-cases are that turquoise, the green values. So those are control values. Where am I going to place this regression, right? Where does the logistic happen? Is it easy for us to put upper and lower boundaries on there? Do we have spaces where we can make easy comparisons? Well, the cross in the center is actually the one versus the rest system for all of the underlying predictors, right? So in the first category, we have systolic blood pressure versus family history. We can see that that has the upper bands and lower bands for the family history characteristic, the binary, split the systolic blood pressure, but don't create any kind of clear categorical, clear categorical. Also tobacco use, also alcohol use, though alcohol use does tend to see a little bit higher on the bifurcation of family history. So this is an acknowledgement of the impact of a binarized input with respect to categorical data, I guess you'd say binarized output of a previous system on the projection of a previous system, or excuse me, a subsequent system. The reason why I say that is this cross line projects the values onto a binary, 1 or 0. All the other of them are continuous, qualitative values, and the central is just a binary value. You either have or don't have a family history, right? that all the other factors, including how much alcohol you drink, right, or how much tobacco use you have, are rated with a scale. So we place those in tiers, right? You smoke 1 to 2 cigarettes a day to 1 to 2 cartons a day, right? From, a beer, in the evening to, a keg, by noon, right? So, I don't know if that's possible, but I'm saying it's like, let's make it insane, right? So, and we also have age ranges, right? But I like to look at this one because I think that it's interesting when you take the respective projection of family history. There are some factors that seem clearly to have pretty good indicators, right? So as age and family history correlate with one another, we notice a high density over here with respect to the end of age and positive family history. That's an easy correlate. We also notice with respect to LDLs, that's cholesterol level, and atherosclerosis, that's hardening the arteries, that as you have an increase in LDL and family history over here, we see a strong aggregate toward positive family history and high LDL levels. Okay? What does this say? Once again, yes?
So is family history just like a yes or no?
Correct.
There's only two.
Correct. It's a categorical value considered in with other continuous values, right? It's a binary value with continuous values. So what happens to it whenever we cross factor them? They just get projected up onto the chance cases with a linear characteristic in class 1 and then a linear characteristic in class 0. So what you're seeing across the top is family history, yes, and then the continuity is a one-dimensional version projected relative to the value of each of the other factors. So low value for LDL on one end, but yes, family history, and then all the way up to high LDL levels. And the third factor that's characterized in each of these slides is the color of whether or not you were a MI victim within the system. So it's an interesting perspective here. One that I think is another acceleration is this data representative of the true system? No, because the true system has a prevalence of 5%. What is this? This would be a prevalence of approximately 30%, maybe even 35, 40%, because it's 160 to 300, right? So it's actually, it's almost, that's actually above 50, right? So that's about 50%. So it would be half, the scale of the MIs is actually half the scale of the controls. So this is a larger influence or a larger indication of the actual scale of MIs that would truly occur. Now, why would we do this? Why would we want to do that? To have a data set that seemed to be more indicative than actually to be representative, right? Why wouldn't I just keep, so if we have 300 samples, right? If 5 per 100 are there, why wouldn't we use 15 samples against the 300 samples, which would be more indicative of the average populational value? Because from a classifier perspective, if I only have 15 samples, what's going to happen? It's always going to say you're in the no camp, right? It's always going to say, no, you're no heart attack. Why? Why can't it learn from those 15 samples? It's just a ratio problem. It's a probability problem. It is the target cases over top of the total cases, right? So 15 samples on top relative to the 317 samples total in the system. Those 15 samples are so small that the system is going to go, the likelihood of you being one of those is so close to 0, or at least is so tiny, 0.1%, right? That I'm going to say, I'm going to err on the side of caution. From an error metric standpoint, these systems do not take into consideration what we say as being phenomenal events. They don't take exceptions into consideration. Our intelligence does at some level. I don't know exactly how we manage that because we haven't really figured out how it works, but we're able to distinguish events that happen with low frequency from high frequency events without losing the thread, right? We can still see value in phenomenal events. We can still see value in anecdotal examples. However, the machine learning systems can't. They need at least something that's gonna pull the weight over to saying that it's beyond just a chance likelihood that you'll even be in that camp. That system, even though you had 5% representation, is not going to output 5% likelihood with respect to how this, when it's going into new data. It's going to err almost entirely on the side of caution by going with the majority class case. Okay, you can replicate this process utilizing these commands, right? So if you want to take this data and mess around with it on your own, you can replicate it. That's the R for that. It's in your book too, and I think it's even one of the supplemental labs as well. All right, so I'm trying to see if there's anything on this slide we need to talk about. I think I already talked about all of it. It said we can output a relative estimated inference sample by adjusting for the control system to estimate regression parameters for the system more accurately by compensating for the offset and scale, right? So we train it with the 160 and 302 cases, right? But what we then do is we adjust the sample from the 0.35 cases provided for the in system, and then, or relative to the whole system, right? So we say it's 35% of all samples presented to the classifier were MI cases, right? It's, when I said 50%, I'm saying relative to the scale of the class, right? So you have 300 samples and you have 150, right? 150 would be half of that grouping. So it's only from that perspective that I say it's half, but it's still, it's a third of the total data, right? It's a third of all total data. We're then going to rescale the third of the total data to the actual event likelihood, right? With respect there, it says the tilde there is a bit like the hat we utilize. It's saying it's a localized approximator, but we're going to rescale that localized approximator to that 0.5 and end up getting a new offset, right? That just adjusts for the difference between the mean of this sample group to the mean of the actual underlying system group. But we have to do it this way. We have to control for the initial case for the 35% characteristic, because if I did try to train it at the representative level, it would be too small to matter, all right? We'll talk about this next time, which is the idea of unbalanced data, right? I've started talking that along the way, right? What we say is that whenever we have more controls than cases, it tends to reduce the variance of the perimeter estimates, right? But after the ratio of about 5 to 1, the variance reduction flattens out again. What does that mean? That means that once I increase the likelihood for the systematic variance, I can end up still having relatively good imbalanced data for the binary output classification, while still reducing the scale of the processing. Right? I don't need as many positive samples in order to be able to provide a relatively good model, but at the same time, I can't have so few samples that the classifier becomes overly biased toward the idea of the majority class, right? So we'll continue on. This continues to be a problem in classification right along. We'll attempt to implement some things that can resolve it and put some metrics together to determine whether or not we have adequate samples from the groupings in play. Okay? All right, thanks guys. We'll see you on Wednesday.
Thank you.
So one question. So is it if I go to R, can I quickly get it?
Oh yeah. Yeah. Well, I mean the labs are written in R, so I mean you literally just copy and paste it over and it runs.
Thank you. But if I face any problem, I will knock you out.
Yeah. I won't. I'm working until about 3:30. So
Just message me when you're free.
Right.
I don't mind at all. I know.
Well, I just wanted to let you know I'm not.
It's all right.
ignoring
It's
you.
all right.
I'll respond when I can.
Yeah, it's all right. I appreciate that. Just you can tell me whenever you want. But we are done for this assignment.
Right. On the next one,
one?
I'm going to start getting here about 9 o'clock. Is there an earlier
And
bus?
I will come earlier also so we can study because this is. I need to
Well, I don't have
structure
time to
myself.
start following up.